Stainless steel is everywhere. From the kitchen sink in your home to the massive pipelines in chemical plants, from hospital surgical equipment to aerospace components soaring thousands of feet above the ground, stainless steel has become one of the most trusted materials in modern engineering. But here's something many people don't realize. Welding stainless steel isn't as simple as joining two pieces of metal together. In fact, a weld that looks perfect on the outside can hide serious problems underneath. A slight mistake in heat control, filler selection, or shielding gas can weaken corrosion resistance, cause warping, create cracks, or even lead to complete component failure. That's why stainless steel welding is often considered one of the most demanding skills in the welding industry. Yet, when done correctly, it produces some of the strongest, cleanest, and most durable joints possible. And thanks to modern welding technology, including inverter welding machines, pulse welding systems, automated orbital welding, intelligent heat monitoring, and advanced shielding gas control, today's welders can achieve levels of precision that were almost impossible just a few decades ago. In this guide, we'll explore what stainless steel welding is, the most common welding methods used today, the biggest challenges welders face, and the best practices professionals use to achieve flawless results. By the end, you'll understand why stainless steel welding remains one of the most respected skills in the metal fabrication industry. Let's get started. What is stainless steel welding? Stainless steel welding is the process of permanently joining stainless steel components using heat, pressure, or both. Unlike ordinary carbon steel, stainless steel contains at least 10.5% chromium. This chromium reacts with oxygen in the atmosphere to form an invisible protective layer that resists rust and corrosion. This protective layer is what gives stainless steel its famous durability. However, it's also what makes welding stainless steel more complicated. Excessive heat, contamination, or poor welding techniques can damage this protective layer, reducing the material's corrosion resistance and affecting its long-term performance. This means that successful stainless steel welding isn't just about creating a strong joint. It's also about preserving the material's unique properties.
Why stainless steel is so popular? Before discussing welding methods, it's important to understand why industries rely so heavily on stainless steel. Stainless steel offers excellent corrosion resistance, high strength and durability, attractive appearance, easy cleaning and maintenance, excellent heat resistance, long service life, and high recyclability. These advantages make it ideal for food processing equipment, pharmaceutical manufacturing, medical instruments, oil and gas systems, chemical processing plants, automotive components, aerospace structures, and construction projects. As industries continue to demand cleaner, stronger, and longer-lasting materials, stainless steel remains a top choice worldwide. Common methods of stainless steel welding. Different projects require different welding techniques. Let's examine the most common methods used today. 1. Shielded metal arc welding, or SMWA. Often called stick welding, SMWA remains one of the oldest and most reliable welding methods. The process uses a flux-coated consumable electrode to create the weld. As the electrode melts, the flux coating generates shielding gases and slag that protect the molten weld pool from contamination. Advantages: affordable equipment, portable setup, suitable for outdoor use, effective on thicker stainless steel sections, performs well in windy environments. Limitations: produces slag that must be removed, requires greater operator skill, lower drag weld appearance, and lower productivity compared to automated processes. Because of its versatility and low equipment cost, SMWA remains popular for repairs, maintenance work, and field applications. 2. Tungsten inert gas welding, or TIG welding. TIG welding, also known as GTAW, is often considered the gold standard for stainless steel welding. The process uses a non-consumable tungsten electrode and an inert shielding gas, usually argon. A separate filler rod is added when needed. TIG welding offers exceptional control over heat input and weld quality. Advantages: extremely clean welds, excellent appearance, precise heat control, minimal spatter, and ideal for thin stainless steel. Limitations: slower welding speed, higher operating costs, requires significant skill, and more expensive equipment. Because of its superior finish, TIG welding is commonly used in food-grade equipment, medical devices, aerospace components, and high-purity piping systems. Modern TIG machines now feature pulse technology, digital controls, and programmable settings that significantly improve weld consistency.
3. Metal inert gas welding. MIG welding, also known as GTAW, uses a continuously fed wire electrode and shielding gas. It is one of the most productive welding processes available. Advantages: faster welding speeds, continuous wire feed, easier to learn, high productivity, suitable for long welds. Limitations: less attractive welds than TIG, more sensitive to contamination, wind can disrupt shielding gas, increased risk of distortion. Today's advanced MIG welding systems use pulse spray transfer technology, dramatically reducing spatter while improving penetration and weld quality. Many fabrication shops now rely heavily on pulse MIG welding for stainless steel production. 4. Resistance welding. Resistance welding includes spot welding and seam welding. Heat is generated through electrical resistance at the joint. Advantages: faster production rates, no filler material required, clean welds, highly automated, consistent quality. Limitations: limited to certain joint designs, high equipment cost, requires proper alignment. This process is commonly found in automotive manufacturing and sheet metal fabrication. 5. Flux cord arc welding. Flux cord welding uses a tubular wire filled with flux material. Some versions also use shielding gas. Advantages: high deposition rates, excellent productivity, suitable for thicker materials, effective in demanding environments. Limitations: produces slag, more cleanup required, higher heat input. Many industrial fabrication projects use FCAW when speed and productivity are priorities. 6. Friction welding. Unlike traditional arc welding methods, friction welding joins materials through mechanical friction and pressure. No filler material is required. Advantages: extremely strong joints, minimal contamination, excellent repeatability, low material waste. Friction welding is increasingly used in aerospace, automotive, and high-performance engineering applications. Modern advancements in stainless steel welding. The stainless steel welding industry has changed dramatically in recent years. Today's technology helps welders achieve better results faster than ever before. Pulse welding technology. Pulse welding precisely controls heat input, reducing distortion while improving penetration and weld appearance. Smart inverter machines. Modern inverter welders automatically adjust current output for improved arc stability and energy efficiency. Digital weld monitoring. Advanced systems can record welding parameters in real time and alert operators when settings move outside acceptable limits. Robotic welding. Robotic systems now perform thousands of precise stainless steel welds daily in automotive and manufacturing facilities. Orbital welding systems. These automated systems create perfectly consistent welds around stainless steel pipes and tubing.
Artificial intelligence integration. Some modern welding equipment uses AI-assisted monitoring to detect defects and optimize welding parameters automatically. These innovations are making stainless steel welding more accurate, efficient, and reliable than ever before. Challenges in stainless steel welding. Despite technological advancements, stainless steel still presents unique challenges. Warping and distortion. One of the most common problems is distortion. Stainless steel expands significantly when heated and contracts when cooled. Improper heat control can cause warping, twisting, misalignment, and residual stresses. This is particularly problematic when working with thin materials. Heat tint and discoloration. Excessive heat can create discoloration around the weld. Known as heat tint, this damages corrosion resistance. Removing heat tint often requires pickling, passivation, or mechanical cleaning. Modern pulse welding technology helps reduce this problem significantly. Corrosion issues. Poor welding practices can destroy stainless steel's protective chromium oxide layer. This can lead to rust formation, pitting corrosion, and reduced service life. Maintaining proper shielding gas coverage is critical. Cracking. If cooling rates and filler materials are not properly controlled. Cracks can form during welding, after cooling, or during service. Selecting the correct filler metal is essential. Welding dissimilar metals. Joining stainless steel to carbon steel introduces additional complications. Differences in expansion rates, melting temperatures, and corrosion behavior can make the process challenging. Toxic welding fumes. Stainless steel welding produces hazardous fumes containing chromium compounds. Exposure can pose serious health risks. Proper ventilation and respiration protection are essential. Best practices for welding stainless steel. Professional welders follow several key practices to achieve high-quality results. Clean the material thoroughly. Contamination is one of the biggest causes of weld defects. Before welding, remove oil, remove grease, remove dirt, remove paint, and remove oxidation. A dedicated stainless steel wire brush should be used to avoid contamination from carbon steel. Select the correct filler metal. The filler material should closely match the stainless steel grade. Using the wrong filler can result in reduced corrosion resistance, cracking, or weak welds. Always consult filler metal specifications. Control heat input. Too much heat creates distortion, burn-through, heat tint, and loss of corrosion resistance. Use the lowest heat input that still provides proper penetration.
Use proper shielding gas. Shielding gas protects the weld pool from contamination. Common choices include pure argon, argon-helium mixtures, argon-CO2 blends. Selecting the correct gas improves weld quality and appearance. Maintain proper travel speed. Moving too slowly increases heat input. Moving too quickly reduces penetration. Consistent travel speed creates stronger and more attractive welds. Prevent cross-contamination. Never use the same grinding wheels or brushes for carbon steel and stainless steel. Even small particles of carbon steel can cause future rusting. Ensure adequate ventilation. Protecting your health is just as important as protecting the weld. Always use local exhaust ventilation, fume extraction systems, and respiratory protection when necessary. Modern welding shops increasingly use smart fume extraction systems that automatically activate during welding operations. Choosing the right stainless steel welding method. The best method depends on your application. Choose TIG welding if appearance matters, precision is critical, material is thin, high-quality finish is required. Choose MIG welding if productivity is important, long welds are needed, fabrication speed matters. Choose SMAW if working outdoors, repairing equipment, portability is required. Choose resistance welding if high-volume production is needed, sheet metal is involved, automation is preferred. Choose friction welding if maximum joint integrity is required, high-performance components are involved. Conclusion. Stainless steel welding is far more than simply joining metal together. It's a specialized process that requires a deep understanding of heat control, filler materials, shielding gases, and metallurgy. Whether you're using TIG, MIG, stick, resistance, or friction welding, success depends on choosing the right process and following proven best practices. The good news is that modern welding technology has transformed the industry. From intelligent inverter welders and pulse welding systems to robotic automation and AI-powered quality monitoring, today's welders have access to tools that make producing flawless stainless steel welds more achievable than ever before. Master the fundamentals, respect the material, control the heat, and embrace new technology.
Do that, and stainless steel will reward you with welds that are strong, beautiful, corrosion-resistant, and built to last for decades. And that's exactly why stainless steel welding continues to be one of the most valuable and respected skills in modern manufacturing, fabrication, and industrial technology. Thanks for watching, and we'll see you in the next one.